Stars. They're big, they're hot, and they are everywhere. Stars rule the universe.
Our destiny is linked to the destiny of stars.
Born in violence, dying in epic explosions. They fill the universe with stardust, the building blocks of life.
Every atom in your body was produced inside the fiery core of a star.
Stars are what make our universe work. All life begins here. The night sky is packed with stars.
On a clear night in the country, if you're lucky, you can see maybe 3,000 stars, but that's just the tip of a vast cosmic iceberg. In our galaxy alone, there are over 100 billion stars. And in fact, there are over 100 billion galaxies in the observable universe. There are more stars than there are specks of sand on Earth.
Every star is powerful, creating the basic matter for everything in the universe, including us. Most are so far away, we know little about them. But there is one star that's really close, and virtually everything we know about stars, we've learned from that neighbor.
The sunlight from our sun that bathes us and warms us every day is nothing but starlight, because our sun is nothing but a star like all the rest.
Seen from Earth, our sun is a blinding ball of light. But take away the glare, and one of the most powerful objects in the universe appears in our own backyard. It's a ball of superheated gas that's been lighting our solar system for 4.6 billion years and dominates all life on Earth.
The sun is 93 million miles away, and that means, in actuality, it's immense. You could fit 1 million Earths inside the sun.
It's nearly 1 million miles in diameter, yet our sun is tiny compared to the really big stars out there. Eta Carinae, over 5 million times larger than our sun. Betelgeuse, 300 times larger than Eta Carinae. If it was our sun, it would reach as far out as Jupiter. And then there's this monster, VY Canis Majoris, the largest star ever discovered, 1 billion times bigger than our sun. Stars burn in different colors, from red to yellow to blue. Some live alone. Others in pairs, orbiting each other. And coming together in huge galaxies, entire cities made up of billions of stars. Each star is a one-of-a-kind. But they all start life in the same way, as clouds of dust and gas called nebulas. Many billions of miles across, they drift through space, forming spectacular shapes. The Flame Nebula, the Horsehead Nebula, the Orion Nebula, Each nebula is a star nursery where millions of new stars are being born. But this birth is hidden from view.
Some of the more dramatic parts of a nebula are not the beautiful glowing gas that you see, but the dark parts. The dark parts have areas of dense gas and dust, and that's where the real action is happening in terms of star formation.
The dust clouds are so thick, regular telescopes can't see inside.
There's nothing more important to us than stars, but for a long time, the way they formed was a complete mystery. We couldn't observe them. Imagine that. We could not see the first moments of a star at all.
Until 2004, when NASA launched the Spitzer Space Telescope.
And liftoff, seeking hidden secrets in the evolution of our universe.
Spitzer is an infrared telescope. It only sees heat. Heat passes through the thick dust of the nebulas, allowing Spitzer to see new stars coming to life inside. These remarkable pictures capture the earliest moments in a star's life as pockets of hydrogen gas begin to heat up.
Any little bit of gas and dust is glowing. Areas that were entirely dark now became bright. We can actually see the very earliest parts of star formation. All you need to make a star is hydrogen, gravity, and time.
Gravity pulls the dust and gas into a giant, swirling vortex.
Gravity brings matter together. And when you bring matter together and you squeeze things into smaller spaces, they necessarily heat up. It's a simple law of chemistry. You compress something, you drive the temperature up.
Over hundreds of thousands of years, the cloud gets thicker and forms a giant spinning disk bigger than our entire solar system. At its center, gravity crushes the gas into a super dense, super hot ball. Pressure builds until huge jets of gas burst out from the center.
That really shows you how violent a process star formation is. These jets are many light years across. Something is literally accelerating material very fast across unimaginable distances.
Gravity keeps the pressure on, sucking in gas and dust particles that smash into each other, generating more and more heat. Over the next 500,000 years, the young star gets smaller, brighter, and hotter. Temperatures at its core reach 15 million degrees. Only at that mind-boggling temperature can atoms of gas begin to fuse together, releasing massive amounts of energy. And just like that, a star is born. It will shine for millions, even billions, or perhaps even trillions of years. Stars produce massive amounts of heat and light over billions of years. But that takes fuel, and lots of it. Until the early 20th century, no one had any idea what this fuel was.
The greatest problem facing physics at the turn of the last century was what drives the energy of stars. All you had to do was look outside and realize there was a huge gaping hole in our understanding. To solve the secret of the stars, we needed a new engine. We needed a fabulous source of energy that could drive a star for billions of years at a time.
And it took a genius to discover it, Albert Einstein. His theories proved that stars could tap into the energy inside atoms.
The secret of the stars is Einstein's equation E equals mc squared. In some sense, matter, which makes up our body, is concentrated energy, condensed energy, energy that has condensed into the atoms that make up our universe.
Einstein showed that it's possible to release this energy by smashing atoms together. It's called fusion, the same force that powers stars.
It's astonishing to realize that the physics of the very small subatomic particle physics determines the structure and nature of stars.
From Einstein's theories, we learned how to release the energy inside an atom. Now, science is trying to simulate a star's energy source to control the power of fusion in a lab. Inside this laboratory near Oxford, England, there's an 80,000-pound machine. Every day, Andy Kirk and his team transform it into a star on Earth.
This machine is called a tokamak. It's effectively a large magnetic bottle, a cage to hold a very hot plasma. We're able to recreate the conditions within a star.
Inside the tokamak, hydrogen atoms naturally repel each other. To smash hydrogen atoms together, the tokamak heats them to more than 300 million degrees. At these temperatures, the energized hydrogen atoms are moving so fast they can't avoid smashing into each other.
If you heat it up, heat is motion, and the motion of hot particles will be enough to overcome the repulsive force.
All personnel be prepared to leave the master machine area.
When everything goes right, the result is the single best power plant in the universe: nuclear fusion. Traveling at 1,000 miles a second, the hydrogen atoms smash into each other and fuse, creating a new element, helium, and a small amount of pure energy.
The hydrogen gas weighs slightly more than the helium. You lost mass in the process of burning. That mass that you lost, the missing mass, turns into energy.
The tokamak can only maintain fusion for a fraction of a second. But inside a real star, fusion continues for billions of years. The reason is simple: size.
The engine which drives a star is gravity. That's why stars are big. Stars are huge. You need that amount of gravity in order to compress the star to create fantastic amounts of heat sufficient to ignite nuclear fusion. That is the secret of the stars. That's why stars shine.
Fusion at the core of a star generates the explosive force of 1 billion nuclear bombs every second.
A star is a gigantic hydrogen bomb. So why doesn't it simply blow apart? It's because gravity is compressing the outer layers of the star.
Gravity and fusion lock horns in an epic battle.
We have this constant tension between gravity, which wants to crush a star to smithereens, and also the energy released by the fusion process, which wants to blow the star apart. And that tension, that balancing act, creates a star.
This power struggle plays out over the entire life of a star. Two awesome forces of nature in a dynamic standoff. As that battle rages, the star blasts out light and heat, but also something far more destructive. Each beam of starlight makes an epic journey. Light travels at 670 million miles an hour. A beam of light could travel around the Earth 7 times in 1 second. Nothing in the universe moves faster. Yet most stars are so far away, their light takes hundreds, thousands, millions, even billions of years to reach us. So, when the Hubble Space Telescope looks into the far corners of our universe, it sees light that's been traveling for billions of years. The light we see today from Eta Carinae left that star when our ancestors first farmed the land 8,000 years ago. Light from Betelgeuse has been traveling since Columbus discovered America 500 years ago. Even light from our own sun takes 8 minutes to reach us. But even before light starts its journey through space, it's already been traveling for thousands of years.
When the sun fuses hydrogen into helium in its core, it creates a photon of light, a particle of light.
That new ray of light has a long way to go just to reach the star's surface.
There's a whole star in its way. And so when the photon is created, it doesn't get very far before it immediately slams into another atom, another proton, another neutron, something. It gets absorbed and then shot off in another direction. And so it's sort of randomly moving around inside of the sun, and it has to work its way out.
For the photons, it's a wild ride, smashing into atoms of gas billions of times as they struggle to escape from inside the star.
What's funny about this whole process is that it takes the photon thousands and thousands of years to get from the core of the sun to the surface. And yet once it hits the surface, it's only an 8-minute trip from there to here.
Photons are the source of light and heat, but they also cause something far more destructive: the solar wind. As they reach the surface, photons heat up the outer layers of the sun, sending it hurtling around the star, creating extreme turbulence and intense shock waves. It's so violent, we can actually hear it. Picked up by the orbiting SOHO satellite, this is the sound of the sun. The speeding gases also generate powerful magnetic fields. As the star rotates, the fields clash and burst through the surface. Giant magnetic loops erupt into space. Some are so large, the Earth could pass right through them, with thousands of miles to spare. They are spectacular, and they are deadly, blasting a stream of electrical particles deep into space. This is the solar wind. It can damage spaceships and satellites, even put astronauts' lives in jeopardy. To discover how the magnetic loops trigger the solar wind, a team of scientists at Caltech recreate the surface of a star, right here on Earth.
It's very exciting to be able to create in a laboratory the same sort of physics that are on the solar surface. We can't go there, we can't even send probes there, but we can try to study what's happening there.
An airless chamber simulates the vacuum of space. An enormous electric current produces a pair of man-made magnetic loops.
The main difference between the plasma loops we make in the lab and the ones on the surface of the sun is just their size. The ones we make in lab are, about this big, and the ones on the surface of the sun can be many times the size of the Earth.
Their experiment reveals that when magnetic loops clash in the lab, they trigger a massive burst of energy. When giant loops collide on the surface of a star, the energy released sends temperatures soaring from 10,000 to 10 million degrees. That extreme heat triggers the solar wind, sending millions of tons of particles streaming out into space. The bigger the star, the more deadly the wind.
If we were orbiting a star like Eta Carinae at the same distance, it would be hell on Earth, quite literally. The amount of energy blasting down on the Earth would strip away our atmosphere, boil our oceans, melt the surface.
Understanding how stars work could help us protect ourselves by predicting their most destructive forces. But there's nothing we can do to protect ourselves when a star dies. In its final moments, it annihilates everything around it. From the moment of its birth, every star is destined to die. Its fuel will run out. Then, gravity will win the battle with fusion, triggering a chain of events that will destroy the star. Our sun is no exception. Every second, it burns through 600 million tons of the hydrogen fuel in its core. At that rate, the hydrogen will run out in about 7 billion years. As the hydrogen gets used up, it slows down the fusion at the star's core. This gives gravity the edge. With less fusion pushing outward, gravity crushes the star in on itself. But fusion fights back, heating the star's outer layers.
When you heat up a gas, it expands. And so the sun will actually expand up. Instead of being 1 million miles across like it is now, it'll swell up until it's about 100 million miles across.
Our sun will become a red giant.
Imagine a sunrise, 7 billion AD. It's not just a little yellow disk coming up all cheerful and nice. What you would see is a huge, swollen, bloated red disk slowly reaching up over the horizon. And when the sun is fully up in the sky, it's blasting down heat on the Earth. It would be like sticking your head in an oven set to broil.
Temperatures here on Earth will reach thousands of degrees.
The oceans will boil, the mountains will melt, and we'll have the last nice day on the planet Earth.
Then, the bloated star will engulf the Earth. But the giant red star is self-destructing. Its core becomes dangerously unstable. With no hydrogen left to fuel it, the star begins burning helium and fusing it into carbon. The star is now destroying itself from the inside out, blasting violent surges of energy from its core to its surface. These energy waves blow away the star's outer layers. Slowly, it disintegrates. The star is dead. All that remains is an intensely hot, dense core. The red giant has become a white dwarf.
By the time a star reaches the white dwarf stage, the fusion process has stopped. The engine has finally come to rest.
Our sun will end its life as a white dwarf, no larger than the Earth, but 1 million times denser.
A white dwarf is a pretty amazing object. It's incredibly dense. If you could take a sugar cube-sized chunk of white dwarf and put it on the surface of the Earth, it would be so dense it would fall right through the ground.
At the heart of a white dwarf, astronomers believe there's a giant crystal of pure carbon. A cosmic diamond, thousands of miles across.
The idea that the sun will become this sort of cool, dark lump of cinder material is kind of sad. But that really will be sort of a trillion carat diamond. Think of that, a diamond in the sky.
But stars can create something much more precious than a massive diamond. When stars much bigger than our sun die, their death is much more violent. But in dying, they create the building blocks of life. Giant stars live fast, burn bright, and die hard. But from their destruction comes life. The death of massive stars creates the building blocks of the universe, the seeds of life itself. Less than 600 light years from Earth, the monster star Betelgeuse is near death. Well, in space years. It's younger than our sun, millions, not billions of years old. But the fusion at its core is far more intense.
Betelgeuse is a different beast from the Sun entirely. It's a red supergiant. And the reason is because Betelgeuse is more massive. It has 20 times the mass of the Sun, and that means what's going on in its core is very different than what's going on in the Sun's.
Massive stars generate pressures and temperatures greater than anywhere else in the universe. The gravity of Betelgeuse is so powerful, it can smash together bigger and bigger atoms. The core of a massive star is a kind of factory, manufacturing heavier and heavier elements, which is what also leads to the star's destruction. Once it makes the element iron, the star is doomed.
In the world of science fiction, there are many ideas about what a star-killer machine might be like. Strangely enough, it's as run-of-the-mill as something as iron.
To a star, iron is the most dangerous element in the universe. It's poison.
Iron absorbs energy. From the moment a massive star creates iron, it has only seconds to live.
The star is trying to dump energy into that iron ball and trying to make it fuse, but it can't. And so that ball is robbing the star of energy, and it's that energy that is supporting the star itself. So as soon as that iron starts to be created in the core, the star has written its own death sentence.
The battle between gravity, trying to crush the star, and fusion, trying to blow it apart, is over. With iron, fusion hits a dead end. Gravity always wins.
The iron core collapses. The outer layers of the star slam down into it, and a huge explosion is generated. Is the single most violent event in the universe, a supernova.
In just a few seconds, supernovas create more energy than our sun ever will.
Within a couple seconds after beginning to make iron, the star explodes in a supernova. So think about that when you're holding one of your iron frying pans. The iron killed a star in just a few seconds. Dangerous stuff.
Telescopes around the world scan the skies for supernovas. In 1987, a brilliant light appeared in a nearby galaxy, 170,000 light-years away. These pictures record the events following the death of a massive star, as a fireball, trillions of miles wide, hurtles out into space. But there's no record of the actual moment of death, when the star first ripped itself apart. The only way to know what happens inside a massive star when it explodes is to make our own supernova.
What's amazing when these stars explode is that they almost turn inside out.
Here in this lab in Rochester, New York, scientists are making a supernova with a giant laser.
Telescopes can't see inside the dying star. With this laser, we can detect the processes that occur as the star explodes. Working with these tools is the most exciting thing I can imagine doing.
This massive machine amplifies the power of a single laser beam 1,000 million times. That's enough power to supply 30 cities the size of Detroit. And all that energy will be directed toward an area the size of a pinhead. Look at this tiny target as a star's core. The laser simulates the most violent explosion in the universe.
This would not be a safe place to be when the laser was fired. If a human were struck by all these laser beams, it would drill a hole right through them.
Now going to closed access in the laser bay. The door is locked. The base is good to get. Final preparations are complete. 5, 4, 3, 2, 1.
The target is vaporized by the laser. The explosion lasts just 100,000th of a second, but a high-speed camera captures the shock wave, expanding outwards.
Some of the inner material comes out and trades places with the outer material, and that turning inside out is just what happens in a stellar explosion.
Material from deep inside a star's core surfs the shock wave out into space. In the extreme heat and turmoil of the explosion, heavier elements are forged. Among them, gold, silver, and platinum. And because there's so little time for the elements to form, they're the rarest and most valuable in the universe.
Silver, gold, everything else are created by the explosion of the star, by the immense energy released, and that's how they come to us.
But even after the universe's most violent explosion, there's something left behind.
We scientists used to believe that after a supernova explosion, a star would literally blow itself to bits and there'd be nothing left. Well, we were wrong. There's a corpse of a supernova explosion, some of the most exotic matter known to science, called a neutron star. Solid nucleonic matter, the most fantastic state of matter in the universe.
The super-dense core is now a neutron star. It's around 20 miles across and unbelievably heavy.
It's incredibly dense. Just a cubic centimeter, just the size of a sugar cube of neutron star material, would weigh as much as all the cars in the United States of America combined.
The dying star doesn't just leave the corpse of a neutron star. It blasts the new elements far out into space. These clouds contain the building blocks of the universe. Everything we know and love is built from this stardust.
Only a supernova has enough energy to fuse these elements which are so essential for life. Without supernovae, there's no life. There's no you and there's no me.
When massive stars die, they seed the universe with stardust. Full of elements like hydrogen, carbon, oxygen, silicon, and iron. The raw materials to build new stars, solar systems, planets, and of course, us. Everything we see around us once blasted out from the core of a star.
You may wonder what stardust is. Well, you're stardust, because every atom in your body was produced inside the fiery core of a star. The atoms in your left hand may come from a different star from the atoms in your right hand, but you are literally a star child.
Long dead stars provided the stardust to create our solar system, the planets, and everything on them.
So you're made of carbon, you're made of oxygen, there's iron in your blood. All of those things had to be generated inside the core of a star. There's no other way to get them. So when you think about star stuff, look around you. Everything that you're made of, everything the world around you is made of, had to come from the belly of a star that blew up a long time ago.
Even the atoms in our own sun are recycled. They're third or fourth generation, leftover debris shot into space by dying stars a long time ago.
Our sun is our stepmother. Our true mother died in a supernova explosion to give birth to the elements which made up our body. But how come the poets and the songwriters, how come they don't write poems to our true mother? It's perhaps they don't understand physics and the laws of stellar evolution.
We live in an age of stars, but it will come to an end. There's only so much hydrogen in the universe. Trillions of years from now, it'll all be used up. And when there's no hydrogen left, there'll be no new stars.
We live in a very brief period in the history of the universe when we still have stars illuminating the sky, stars creating life as we know it, but it's not going to last forever. Sooner or later, the stars will begin to blink out.
First, the massive stars will burn out. Then, mid-sized stars, like our sun, leaving only the smallest. Trillions of years later, they too will fade away.
Slowly, inexorably, the universe will get colder and darker until the last star burns out and the universe becomes dark once again.
The age of stars will be over.
Honestly, the future of the universe looks kind of grim, but you can take something positive out of that. This is the best time to be alive. This is the time where life can flourish, stars can form. We are in the golden age of the universe right now.
We live in a season for life in the universe, if you will, that lasts for a few billion years. And that makes me at least appreciate the way things are right now, because they weren't always that way, and they won't always be.
We live on the stage where stars glow and illuminate the night sky. When stars create life as we know it, we live in the best of all stages of the universe.
For now, stars will continue to shape our universe, generating the building blocks of new worlds, creating new stars, and filling the darkness with light.